All right, well, my talk is about metacognition for power management in autonomous systems. It's a bit more applied than theoretical in comparison to the other talks today. The model that we're working with is a undersea drone, which requires some serious power management capabilities. So I'll start off just by referring to the reasoning. So the reasoning for this talk and why we want power management is the undersea drones that we're working with are intended on going on extremely long missions, maybe months at a time. So this is an extremely power sensitive sort of vehicle that we're working with. And when it's undersea, it doesn't really have solar panels. So current power management solutions for microprocessors were designed for laptop and desktop environments, and not really that applicable to these autonomous systems. Also, power management provides a starting point for more advanced metacognition services. So this is a way of getting the metacognition into the autonomous agent and providing that framework, which can then have other capabilities added in. So the current power management system in chips is called dynamic frequency scaling, or it's dominated by dynamic frequency scaling, which is the system which decides when to upscale or turn on cores a laptop or desktop CPUs. It functions on what's called an activity factor, which represents the average amount of switching done by the transistors on the chip. Now, in an autonomous system, we're really going to want to max out the CPU resources all the time. Even when we've got good plans, we really want to be on the lookout for any sort of unexpected events. We want to be optimizing those plans. We just want to be crunching numbers all the time to make sure that we're doing the absolute best. And this doesn't really gel very well with dynamic frequency scaling. So the existing power management systems will just be running the CPU at full power all the time, and that's not going to do any good for our power management and our battery life. So we decided to look into other alternatives. And just for our reference, the hardware that I'm referring to in this talk, although it's not completely restrained to this hardware, is the NVIDIA Jetson TX2. The TX1 is also extremely similar, so that will work the same. It's a quad-core ARM board. In the picture there, that's the development version. It's got 8 gigs of RAM. The TX1 has 4. And for an operating system, we'd be considering to use any sort of minimal Linux distribution. Doesn't really matter. Similar. And Moose IVP for the middleware, which doesn't come into it too much, but it does provide options for inter-process communication. So just briefly, when is the metacognition power management required above and beyond the dynamic frequency scaling? So low battery states is a good one. For example, if the battery is running extremely low and we are a distance away from our rendezvous point, we're going to want to really keep our decision-making narrowed to getting home. We're going to want to leave as much off, and we're not going to really want to ramp up the amount of processing power and drain the battery. Even if something interesting happens, we really want to keep on track and make sure we get home. Alternatively, we've got periods of low computational needs. We've got our plans sorted. We're just traversing the ocean for maybe days or weeks on end. And we don't want to be using up all of our battery power really refining our plan or being extra alert for any unexpected events. And on the flip side, we've got periods of high computational needs. These are times when maybe a couple of unexpected events have occurred at the same time as we were replanning, and we really want to give all power to the CPU and the autonomy agent at once. Now, our capabilities, what does the metacognitive loop actually have access to modify the power draw of the autonomy agent. Primarily, it can modify the active core count in the TX2 reference board I'm using. That's got 4 chips with which it can set its core count from 1 to 4. It can set its core clock frequency. So it can scale the amount of power going to the chip to increase its gigahertz. And it can modify its GPU, which is a reasonable portion of the TX2. It can restrict to a low power core only. That's something that's fairly special in the TX2, but is becoming more common. And it can switch off external I/O ports such as HDMI. Now, that's something that we really have to deal with on commodity boards. Specialist hardware, that wouldn't be an issue, but commodity boards are perfectly fine for the job. We just have to make some considerations. And lastly, fan control. We wouldn't be expecting to use a fan control in undersea operations, but if it's a surface or a ground vessel, you're most likely going to be running a fan. And configuring the speed of that will extend your battery life. So on the actual practical side, how do we switch those CPU cores on and off and modify their frequency from our program? So using a Linux distribution, we can merely send variables to paths in the Linux file. The first step is to send user space to the scaling governor. This just switches the device from an automatic power management system, which I've already explained is not very applicable for a autonomy agent. So it switches it over to manual control, or in reality, it's switching it over to automatic control, but it's controlled by the metacognitive loop rather than the system's inbuilt power scaling, which has no comprehension of the actual use that we're using the CPU for. To actually send the message to send to set a CPU core to either on or off, we send 0s and 1s to the online path as well. Continue on a little bit more, we can get a dynamic list of CPU clock frequencies by interrogating the scaling current frequencies. And we can then use that numbers from the list of numbers that gets returned and set the CPU frequency by sending that number to the scaling max frequency file path. Now the TX2 has a low power core. This is extremely relevant for these sort of long duration undersea sort of missions. And to enable this, we just simply switch cores 1, 2, and 3 off. Core 0 has the capability to switch into an extremely low power mode, which has a 51 kilohertz minimum speed. So that's what we'd really want to have, just to keep an eye on our sensors, make sure nothing unexpected happens when traversing for days or weeks at a time. Now, the capabilities that are not available, things that draw power that we're not actually able to modify. It'd be great to disable portions of RAM when they're not in use, but that can't be done. Sensor power management, such as GPS or sonar. These are big power draws, but as the metacognitive loop, you could take 2 approaches here and either have a metacognitive loop that has complete and utter vision of the cognitive loop and has a whole lot of code and is a very complex metacognitive loop, but that then controls power to the GPS and sensors. But I think it's far more rational to control the power to GPS and sensors as part of the resource management in the cognitive loop. And lastly, the actuator resource management. So that falls under the same umbrella as sensor power management, in that it's really only the cognitive loop that knows the best resource management for that. And adding that capability into the metacognitive loop is really duplicating resources here. So to touch on interprocess communication, what's the easiest way to communicate between the cognitive loop and the metacognitive loop? So in this extremely low power sort of environment, we want something that is simple to implement in code, and once again, doesn't really use any low-level kernel calls that might actually chew up some clock cycles there. So a named pipe is quite a good option. It's straightforward to implement in code, very little extra code that may result in bugs, has very low computational overhead, and no file system access, which falls into that Linux kernel that before. The only real downside is it's unidirectional. That requires a cognitive process will need to subscribe to a separate pipe to receive messages back. But in most cases, for power management, that won't be necessary. Now, the other options, just to quickly cover them, are to use files for process synchronization. This does require calls to the kernel's API, which of course adds more CPU usage. So that's not a good option. We've got more advanced versions of interprocess messaging, such as sysv, provides a lot more capabilities, but once again creates overhead, and we don't actually need a whole lot of intensive communications to enable a power management process. Next up, we've got an autonomous pipe, which is also a good option. It does require each process to have access to the handle for the pipe, which of course requires something like a calling function that forks off both the metacognitive and the cognitive processes. And lastly, shared memory. It's also a very good option, requires semaphores, but you're not doing any sort of file system accesses. You're not creating any more required clock cycles. And so if you're linking your metacognitive loop to your cognitive loop using shared memory, that's a perfectly fine way of communicating that information back and forth for this purpose. So next up, the power management policies. So what actual approach should the metacognitive loop be taking to rationing out the power to the CPU in response to the signals it gets from the cognitive loop? And the two main approaches here are the absolute simplest, which is to maintain a constant iterative rate. That is to keep a watch on how long it takes for the cognitive loop to perform an entire loop through the MIDCA loop, and vary the CPU power up and down to maintain a constant rate. And secondly, to control a variable iteration rate, that requires a bit more communication between the cognitive loop and the metacognitive loop, but provides some benefits I'll cover shortly. So just quickly, the constant iteration rate turns on power if it notices that the MIDCA loop is taking longer than it used to, and it turns off power if it finds that the MIDCA loop is taking less time than it used to. It's pretty much that simple. The benefits are it's extremely simple. The desired rate can be determined in a number of ways depending on the complexity of the domain and the optimization of the cognitive loop. Scales well with new hardware, very little work to move to new hardware or different planners, and it works with pretty much any sort of cognitive loop or any components in that cognitive loop. Downsides, it does not respond to dynamically changing needs. So it's going to give your system a very, very good overall performance that's hardware independent. But on the downside, when your system could really benefit from some higher level, some faster thinking, or when it's really reversing those long haul sort of trips, it's not going to be hitting the maximum optimization for the power management there. And the desired iteration rate must also be decided before the mission starts, which makes it a little bit difficult, but not in complete end goal there. So, sorry, the variable iteration rate. Now this responds to the state of the cognitive loop and varies the desired iteration rate while in the field. So it requires a little bit more communication from the cognitive loop above the length of time that the MIDCA loop took to actually process. It requires some more information along the lines of how many goals don't have plans for them, how efficient the cognitive loop thinks the current plan is, how many unexpected events are currently occurring, basically an all-round stress sort of variable, the amount of stress that the cognitive loop is currently under. And it uses this stress variable to provide more resources and increase the iteration rate when under stress and decrease it when not. So this allows the dynamic power allocation for those situations where faster computational time is actually going to be needed. Now, its downsides, when compared to the constant iteration rate, is that it requires a larger amount of communication between the cognitive loop and the metacognitive loop. That requires a bit of work to be done in the cognitive loop to implement this stress variable. And even a basic stress variable is really going to be quite beneficial here, in that it's going to allow the variable iteration rate metacognitive loop to provide power when necessary. And a more complex stress variable is, of course, going to be beneficial, but you're going to see quite a lot of benefit just from a basic stress variable. So just to sort of round up with the discussion here, the reason that we would put this in a metacognitive loop rather than a cognitive loop is mainly because this allows the people running the cognitive loop to focus purely on providing the absolute best cognitive service, completely absent of any knowledge of the hardware it's running on, and leaves the metacognitive loop to actually provide the power to the cognitive loop. And at the lowest level, a constant iterative rate will work with most planners, but a variable iterative rate with a stress variable being communicated to the metacognitive loop is far more desirable. And when sort of taking this sort of power management approach, pay attention to the other processes running on the system. Even the minimal Linux environments are often can often be cut down a little bit further for these incredibly power-intensive scenarios. And there's quite often a bit more that can be hacked and slashed out of the kernel. And that is the lot.